Yes, I can.
Okay. You have some questions for me or anything you want me to go over, discuss, or help you with?
Yeah, the stuff on like photosynthesis and respiration.
Okay, so the carbon cycle.
Yeah.
So, okay, so let's see. So we know that respiration and photosynthesis are opposites. Does that make sense?
Yes.
Okay, so one runs one way to store really energy, the other runs the other way back to release the energy. So photosynthesis captures the energy from the sun. It's kept in that glucose. And then the animals, plants, fungi, bacteria can all release that energy completely with oxygen. So if you take a look at them, the inputs for one are the outputs for the other. Have you noticed that yet?
No, I have not.
Okay, so we start out with photosynthesis. See if I can make this work on the board here. So we're going clockwise. That's kind of arbitrary. So we got photosynthesis. And respiration. We can go clockwise, counterclockwise. It doesn't matter. Circles are run in both directions. Is that visible to you or not?
Yeah, I can see it.
Okay, so if we take this side and go clockwise, the inputs to photosynthesis, we have water, chemically called H2O, if you had chemistry.
Yes.
Okay, so these symbols make sense to you, right?
Yeah.
Okay, so, and carbon dioxide. So CO2 there. So photosynthesis takes those, they use those to capture the energy from the sun. And then coming out of that, we have glucose, which is our carbohydrate, C6H12, oxygen 6, plus oxygen. So this is how our planet got all its oxygen, O2. And I think if you do the math there, I forget how many we have to do of each, probably 6 and 6, that makes 18 oxygens. So I think it's 6 carbon dioxide, 6 waters, and then we create 5 oxygens at the other side. You don't have to remember that, but just so you know. Okay. And then if we want to start respiration, we take that glucose, we take that oxygen, and the outputs for one, carbon dioxide and water are the inputs for the other. Respiration allows us to release the energy where we most need it. So it's saved in that carbohydrate, the plant, the animal, the bacteria can release that energy stored in glucose for whatever use it has.
Okay. Yeah. Next to glucose on mine says like carbs. Is that part of it or no?
Glucose is a carbohydrate.
Okay.
So that's a subset. So glucose is the first thing. So we could say also called carbohydrate.
Okay.
Glucose is the basic building block from which all other carbohydrates are made.
Okay.
Does that clarify things?
Yes.
Okay. Anything else related to the carbon cycle?
I don't believe so, no.
Okay, is this going too fast or too slow?
No, it's perfect. It's fine.
Okay, just checking.
The stuff on like sampling and like the frequency of analysis,
Uh-huh.
I didn't really understand that.
Okay. So we're trying to discuss good sampling technique. That's the important part of that. So we went through a process for sampling. Does that make sense?
Yes.
Okay, and then we talked about sampling frequency, and that you work with your nutritionist, decide how often things are sampled. Do you want to sample them, once a month, every few months, once a week, whatever seems to work? And the frequency of sampling, or how often you should sample, is related to variability. So things that are more variable or more uncertain, we have to check more often. The things that we're pretty confident about, we can sample them once and let them rot, let those results stand for a while before we go back and check.
Okay.
So that would be the summary of that. Why do we sample, or when do we sample? When the nutritionist tells us to, and that reasoning that the nutritionist should use should be related to how variable things are. The more variable, the more we sample.
Okay.
Does that make sense?
Yes.
Does that clarify that? I think one slide there where we kind of went through things.
Yeah.
So that's the main idea. You should have taken from that slide. I apologize for not making that as clear as I could have.
I'm just trying to find other stuff that I was confused on.
Fair enough. We've got a whole hour here, and I'm guessing 2:20 at 2 o'clock is not going to show up. So you might have an hour and 50 minutes. So.
The stuff about the disaccharides, polysaccharides, monosaccharides.
So we're showing you that carbohydrates, they basically fall down to, or summarize to, a pretty simple formula: 6 carbons to 12 hydrogens to 6 oxygens, or a 1:2:1 ratio. But that ratio can be expressed a number of different ways, as simple as glucose or fructose. Or we take a couple, we stick them together, or you got starch, which is hundreds of thousands of glucoses in a row strung together.
Okay.
So we start out with the monosaccharides. Those are the simplest. We go to disaccharides. That's the next level of complexity. And then we go to the very complex ones, which is the big and most complex, most varied in shape. As you can imagine, one glucose, you can't, there's two shapes it can be, whereas with starch, there are infinite number of shapes it could be. And that helps with, we talked about digestibility and fermentability and things like that later on.
Okay.
Does that help?
Yes.
Does that answer your question?
Yeah.
Okay.
So, the soluble and insoluble stuff.
Okay, so we're starting out with the detergent system.
Okay.
So the detergent system is, we put things into different categories based on their solubility. What goes into the detergent solution, what does not. And that solubility, whether it goes into solution or doesn't go into solution, is very much related to its availability to the animal. The faster it goes, the easier it goes into solution, the more available it is to the animal. So this is, the detergent system is a system of analysis that is very much related to the biology of digestion. Whereas systems previous to that did not reflect what our cows do as well as this detergent system does.
Okay.
Does that make sense as an overview?
Yeah.
Okay, and then there's 3 different solutions that we're dealing with in the detergent system. We have neutral detergent, basically soap at pH 7, neutral. Then we have acid detergent, which is soap at pH 2, which is close to battery acid. So you see that that's a much harsher solution. It's going to be more aggressive about ripping things apart, about solubilizing things. Then the last one is that 72% sulfuric acid. Very aggressive, you know, it'll dissolve a hole in the floor. And then we deal with so what's soluble and insoluble. So if we're thinking about NDF, do you know what the constituents or what things are in NDF?
Fibers.
They are the fibers. Yup, it's the cell wall. Do you know what that cell wall is made up
of? Sugars.
Sugars, ultimately, how are those sugars arranged? What are those sugars arranged in complex carbohydrates? Hemicellulose, cellulose, and lignin.
Oh, okay.
And then if we talk about solubility, so we've talked about water soluble. We've talked about ND soluble and AD soluble, and then that lignin, that H2SO4, 72% soluble. So if we're just dealing with water, we've got partial. So the cell contents would be partially water soluble. We talked about that later when we talk about carbohydrates. We've got not, and not, or no, as the case may be. NDF, all of the cell contents are soluble,
Okay.
but not hemicellulose, cellulose, or lignin. So hemicellulose, cellulose, and lignin make up NDF.
Okay.
So what would be another name for the carbohydrates up here? If this is all NDF down here, what is this?
Sugars.
Sugars. What else might be up here in a carbohydrate sense?
Starches.
Starch.
Protein.
And protein will also be there, but that's not a carbohydrate. So you've got all that. So the sugars, starches, and we throw in organic acids as well. What are those called as a group of carbohydrates?
I'm not sure.
So we can either call them non-structural carbohydrates or non-fiber carbohydrates. Does that ring a bell?
Kind of.
Kind of. So we have a division here where everything down here is NDF. Everything up here is non-fiber carbohydrates.
Okay.
So we're splitting what is soluble, what is not soluble.
Okay.
That helping make sense?
Yeah.
Okay, and then we go down here with the acid detergent solution. All the cell contents are still soluble, plus the hemicellulose, but not the cellulose and the lignin. This, we can't digest this at all as humans, but the cows with their rumen can ferment that with the bacteria.
Okay.
So that becomes harder and harder to get a hold of. This is in between. This is relatively easy. Then that last step, all the cell contents, all the hemicellulose, all the cellulose, but not the lignin. Is that way of expressing it make things a little easier to understand for you?
Yes, it does.
So if you really want to throw a wrench into this, you could add pectin, which we really didn't talk about this class, so this is bonus. If it gets confusing, just skip it because it won't be on the test. But pectin is not soluble in water. It is soluble in ND. It's not soluble in acid detergent and is in there. So it tends to act funny in this class or in the detergent system. So that's why I really haven't talked about it. But if you're interested, that's one less thing there. So that's why we do the NDF first. It comes out in the non-fiber carbohydrate, and then we do the acid detergent second. So we only get cellulose and lignin left over, not cellulose, lignin, and pectin. So we have to do a sequential NDF analysis for our legumes where that pectin is present.
Okay. The energetic efficiency stuff.
Okay.
Like the aerobic and anaerobic.
Okay. So if we go back to our carbon cycle, what did we say for respiration to be complete? What do we have to include? What are the inputs to the carbon cycle for respiration?
So it's the opposite of photosynthesis, so it wouldn't be the water, CO2, and sun. It'd be the opposite of that.
Be the opposite of those. Those are the outputs for respiration. If we want to take our carbohydrate or glucose and burn it all to CO2 and water, which is the output from respiration, what do we need to burn that? What else do we need to burn that carbohydrate all the way to CO2 and water?
Glucose?
You've got glucose as the carbohydrate. What else do you need?
Oxygen.
Oxygen. A fire does not work if we don't have oxygen. So in the rumen, is there any oxygen?
No.
No. So we can't do respiration in the rumen. We can't burn all the way to CO2 and water and extract all the energy out of it. So the cow, by saying that the rumen is anaerobic, will allow the bacteria to unlock the NDF, chop it up into little pieces we call VFA, but they can't burn that VFA all the way to CO2 and water to extract all the energy. Does that make sense?
Yes.
So they have the oxygen there. The cow keeps the oxygen in, it limits what the bacteria will do. So in order for them to get their energy, they have to continually unlock NDF, turn it to VFAs, and do a whole lot of it because, you know, breaking glucose into like 3 acetates will only give them partial amount of energy. So I think I said 2 to 4 ATP per mole.
I think so.
Like
Yeah.
something like that. Versus if we take that glucose and we run it completely through respiration in the presence of oxygen, you're going to get like 34, 35, 36, 38, depending on the energetic efficiency. So you're looking at something that's like 10 times more energy released with oxygen present. So the bacteria take about 10% of the energy from that cell wall. The cow gets the rest of it, the other 90%, by not allowing those bacteria to have oxygen.
Okay.
Does that make sense?
Yeah, a lot more sense in my notes.
Okay, so I think at the bottom of the one slide there, it's, you know, by limiting the oxygen, the cow, most of the energy is retained in the VFAs, which the cows have to use. And that's where their cows make their living energetically off of the VFA. So the unlocking process costs by the bacteria, they charge 10%, just like a sale charges 12% or whatever. You're going to use my services is going to cost you. So the bacteria get 10% of the energy and the cow gets 90%.
Okay.
Does that make sense?
Yes.
If we had all the oxygen there, then the bacteria would get 100% of it because they don't care about the cow ultimately. That's what happens if you link that to the silage in the feed out phase. We've got the molds and the yeasts have access to oxygen again. They are burning all the carbohydrate and everything else to CO2 and water. They're stealing everything from the farm if we let that face get oxygen, or that silo get oxygen.
Okay. Is there going to be like equations on there, like the stuff we did in lecture 10?
And those energetic things?
Yeah, for like
I'm not
DMI.
going to ask you to memorize those equations. If I was going to ask you equations, the ones that are fair game are how to calculate dry matter.
Okay.
And how to calculate dry matter intake.
Okay.
Those big chemical equations, no, you don't have to memorize those.
Okay.
Closest I'd ask you is how many carbons does an acetate have? How many carbons does a propionate have? And how many carbons does a butyrate have?
Okay. The stable phase.
Uh-huh.
Like what? Like what does it mean by like when it says the biosystem depends on, like what exactly?
That means nothing's happening, more or less.
Okay.
So it's a fancy way of saying that you reached a point where not much is happening biologically. So
Okay.
fermentation is all about picking certain microbes that are helpful to us, whether we're making silage, beer, soy sauce, whiskey. We pick the microbes that we want to do whatever process that we want them to. And then, we try to get it to a stable phase at some point. So what are the characteristics of the stable phase?
Air penetration, remaining soluble sugars, fermentation acids, presents, and like yeast molds.
Okay, so breaking those apart, in the stable phase, we've generated all the acid we need to preserve the forage. What does that acid do to all the bacteria and molds and yeasts?
Does it break it down?
It will kill them. So that's a form of breaking down. It'll either kill them or put them in dormancy where they can't do anything anymore. So basically, we're shutting down all the biological processes because other bacteria have generated so much acid. So hopefully we're down in that pH 4, and we've generated a lot of lactic acid and a lot of acetic acid that's going to hold that pH down.
Okay.
As long as oxygen remains out of that stable silage, it will not change. It can stay for years.
All right.
But once the oxygen comes in, the dormant yeasts and molds say, well, I can slowly turn that acid into something. And as they, with oxygen, respire those acids to CO2 and water, what happens to the pH?
It goes up.
It goes up. We don't have that acid inhibition anymore. And the microbes, the yeast, the molds, the bacteria go nuts. And they start stealing all of they complete the carbon cycle back to CO2 and water. They steal everything that we work so hard to preserve.
Okay.
So that's one of the ways we're using the carbon cycle this semester.
All right. Hmm. I'm pretty sure I know most of the Joe's rules.
Okay.
That's just basically like the 3 priorities, right?
Yep.
Okay.
So that's a more colloquial way of remembering maintenance is always first. Taking care of my current calf is second. Producing milk and then getting pregnant again is third. So if we're doing farm analysis, if she's got enough calories after taking care of herself, she will produce milk to feed her calf. If she's still got enough calories left over, she will reproduce. So we'll talk about more if you take 220, that one of the first things, if your nutrition is off and you don't have enough calories, one of the first things that to go is reproduction.
Okay.
Because she doesn't have enough calories to get things done.
All
So
right.
reproduction either stops or is very delayed.
And I think the last thing that I was like a little iffy on was the energy and feed stuff, like the gross energy, digestible energy.
Okay.
Like those, they still confuse me, like, and how they work, or what goes into what, and all that.
Okay. So okay, so going back to that, we have that, like in that one diagram we had about a chicken eating a certain amount of feed, and then from the energy in that feed, where does that all go? So we know that the cow, good digestibility for a cow is about 50%. Chicken is going to probably be closer to 60 or 70% because they're eating diets that are high in cell contents. There's very little fiber in their diets.
Okay.
But a cow is going to make her living off of fiber, off of NDF. And what are the reasons we said a ruminant might do that? Do you remember?
I do not know.
Okay. If you're looking out into the world, why would a cow choose to eat grass as opposed to something else? Or cell wall as opposed to something else? Looking out here, all we see around us is cell wall. It's an abundant food source. It's going to take a lot of work to process it and make it useful. We have to have that rumen fermentation where the bacteria unlock everything. They make protein. They do all that stuff that's helpful to the cow. But the cell wall is very, very abundant. So that's why she picks that strategy. But she's only going to get about half of it digestible. So we're going to have half of the calories that go into a cow are going to go right through the animal. So we're going to have a certain amount of fecal loss. With a cow, that's going to be about 50%.
Why does it go just straight through them?
Because they can't extract the energy between the microbial work in the rumen and her work as a small intestine. So there's an awful lot of NDF that passes through the animal that is never made available.
Okay.
Because it's tough to get calories out of it, but you're looking at a diet digestibility, let's say 50%.
Okay.
So the other 50% of the calories are going to be stuff that's digested. Now, some of that stuff that's digested, but not available to the cow, is stuff that kind of is released through digestion, but goes in different directions and the cow can't get any of it. So we're looking at gas loss. Is that readable to you?
Yeah.
Okay. And urine loss. So we're looking at gas. Digestion with our cows generates methane. Methane has a lot of calories in it, but those calories cannot be extracted by the cow. The only way we can use them as humans is to light it on fire.
Okay.
So there's the same thing. There are a number of compounds that are extracted from the feed, digested, but they get absorbed and they go right to the urine, and the cow never gets a chance to use those. So you've got fecal loss, sulfuric gas, and urine. What we have left is the energy available to the cow. We started out with this much. We're down to here. With me so far?
Yes.
Okay. So there's two different ways that rest of that energy can go. As we convert it from one form to another, there's a certain amount of heat loss. We call that, I guess I should give you the formal name of that so it matches your nose. It's called heat increment. So just like when we pass electricity through a coil on a stove, there's a certain amount of resistance, so energy is lost that provides heat for us to cook with. But the other rest of the energy goes all the way through the circuit. And then this is available to the animal to do whatever she needs to.
Would that be like net energy?
That is net energy.
Okay.
So either for maintenance or production. That makes sense?
Yes.
Okay. Now, so this from here to here is the gross energy of the feed, all of it.
Okay.
From here to here is the digestible energy, all that stuff that gets digested and available, extracted from the feed, does not go out the back end of the animal.
Okay.
The next step is metabolizable energy. That includes heat increment and the energy available to the animal. The last step is the net energy. So it might help if you start with, gross energy is all of it, right?
Yes.
The other three go in alphabetical order. DMN. Did you notice that already?
No.
Okay. So what will happen here is you have an animal in maintenance. Some of this heat can be used to keep her body temperature for a cow at 101.5. So this will cheat out for net energy maintenance. Growth is not nearly as an efficient process as maintenance. So taking the ME, the NE will be less extracted or used to do something. This becomes net energy growth or gain.
Okay.
That's less efficient. We capture less energy in growth than we do with maintenance, and that's because we can use some of that heat to maintain body temperature. That makes sense?
Yeah.
So net energy maintenance for taking energy out of the feed is more efficient than our net energy growth. And then our net energy lactation, since we're just transferring some things, it tends to be more efficient than our growth. So we extract more of the ME in our net energy lactation.
Okay.
So I've said in class, I don't know if you saw about this, you can think about this also. Best analogy, at least for me, has been this. You can think about it as gross pay, right? Are you being paid under the table, or you go to a place that takes all this stuff out of your paycheck?
Yeah, I get all the stuff taken out of my paycheck.
Okay, so over here is the net pay. So what are our losses along the way? Well, the government's going to take a bite. So let's say this equals, I like thinking about fecal losses as federal taxes. That's just my sense of humor. And then we have state taxes. Are you in New York or New Jersey?
New York.
New York. So these are New York taxes. They take their cut. And then you have Social Security for heat increment. Does that help?
Yeah.
So you're thinking about your gross pay. That's all the money you've earned, but you only get to keep or use a certain amount because you have to pay these tolls.
Oh, okay.
So with net energy, the animal only gets to use a certain amount because we lose stuff along the way. We lose things. We aren't 100% efficient at each step. So gross energy versus net energy. Net gross pay versus net pay. That's the best analogy I can come up with for that. Does that help sort it out?
Yeah, that makes more sense now.
Okay. So, and if we did a tree diagram, we presented that in class. Let's go crazy and get another color here. So branching things off. Gross energy, and then we do things in alphabetical order. D, E, M, E, N, E. So what do we lose from here?
The
Fecal losses is our first cut. What do we lose here?
the gas in urine.
Gas and urine. And then what do we lose here?
The heat.
Heat. So you can think about heat increment. If you're like me at Thanksgiving, you kind of go nutso. Because I really like Thanksgiving and the big meal and all that stuff. You sit down after that meal and you just feel that heat coming out. You get all warm and sleepy and all that stuff. Part of that is heat increment.
Okay.
So if we start to think about this, how could I define digestible energy using these other terms? How could I define digestible energy?
That equals gross energy minus the fecal loss.
So gross energy minus the fecal loss. What if I was using ME to describe?
It equals digestible energy minus urinary and gas loss.
No. You got the right two terms, but what's the sign? I'm asking you to define digestible energy using ME. So that would be ME plus urine and gaseous loss would equal digestible energy, moving back up.
Okay.
So if I was going to define DE using NE, what would I do?
It would be Ne plus heat increment and gas and urine loss.
Yep.
Okay.
So being able to go up and down on that scale.
Okay.
So NE is what defined by gross energy?
It's plus the gas and urine loss and fecal loss.
You'd have to subtract those. So gross energy minus fecal loss minus gas and urine loss is going to give me ME.
Okay, so I just went backwards with it.
Yep, you just flipped your sign. So, you know, if you did gross energy divided by NE, it'd be NE plus heat increment plus urine gas plus fecal losses equals gross energy. Or your net pay plus Social Security plus state taxes plus federal taxes equals gross pay.
Okay.
Does that help?
Yes. That does help.
Okay.
I honestly think that's about all that I had questions on.
Okay. Well, you'll have an opportunity again tomorrow if you want to.
Okay.
So we're doing 100 at 1 o'clock again tomorrow. And then I'll try to have an open session if anybody wants to stop by for a brief question, 6 to 9 tomorrow night.
Okay.
Okay.
All right. Thank you.
You're welcome. We'll try to get this posted, these pictures and stuff posted. I've been recording here. I assume you saw that.
Yeah.
The other students asked me to record this and post it. So I'm going to try to do that up on YouTube.
All right. Thank you.
You're welcome. I hope that was helpful.
It was.
Okay. Have a good day.
You too.